Hey there, awesome physics students. Let's do an example problem with three boxes being pushed that use both Newton's second and third law and show the consistency between the second and third law. So here's the situation. We have three boxes. Box 1 is 15 kilograms. Another one, number 2, is 8 kilograms, and number 3 is 5 kilograms, and they're being pushed by 70 Newton force. And the things we want to find are the overall acceleration for the trio of boxes. And we also want to know what these internal forces here are between the two boxes. So we want to know the force that box 2 exerts on 3 and the force that box 1 exerts on 2. Okay, so let's get started. I've drawn a picture here already. Let's draw some free body diagrams. Which ones do we start with? Well, what I want to start with is the overall free body diagram for the whole thing, the total mass. And the total mass is going to be 28 kilograms. Okay, so the forces on this 28 kilogram box, if we consider it as one big unit, are 70 Newton push force, that's external. And then we have the total mass of the box times G, which gives us the weight of all three boxes. And then we have the normal force pushing up on from the floor. And those two we're not going to worry about too much. It's mostly the 70 Newton box that we want to know about. So if I push all these three, they're going to be accelerating in this direction to the right here. So I want to use a standard XY coordinate system, and I'm going to concentrate on just the X direction here. Okay, so let's go ahead and sum the forces in the X direction on this. And that gives us a positive 70 newtons because that points in the positive X direction. That's the only force in the X direction. And so then I set that equal to my total mass times the acceleration in the X direction. So I can find my acceleration because I know this mass is 28. And so if I do this, I find that the acceleration is the 70 newtons divided by the 28 kilogram total mass. And when I compute that value, I get 2.5 meters per second, or meters per second squared. Okay? So now I know this one is 2.5 meters per second squared. Okay, so that's good. I've got one thing already. Now I need to get these internal forces between these boxes. So let's start with this one. I think that one is the easiest to think about. Let's draw box 3 over here. That's the 5 kilogram box. And it's going to feel a normal force, and it's going to feel a force due to gravity, which aren't going to be terribly important in this case. And it's touching box 2 here, the 8 kilogram box. And that box 2 is going to push box 3 this way. So that force, that's the force from 2 on 3. Okay, that's one of the things we want to find there. All right, so I know my acceleration is again in that direction, and I know what the value of my acceleration is, 2.5 meters per second squared. So let me go ahead and sum the forces in the X direction here. For this one, that's the force of 2 on 3 is the only force, and that's equal to the 5 kilogram, that's mass 3 times the acceleration, but I know the acceleration is 2.5. So this gives me 5 kilograms times the 2.5 meters per second squared. And when I go ahead and compute that, I get 12.5 newtons. Okay, so this tells me that this is 12.5 newtons. Okay, so now I know that one. Now, how am I going to get the forces on this box? Well, let me just draw the free body diagram for box 2 here. So I'm going to have force of gravity and the normal force as usual. And it's touching box 1. Box 1 is going to push it this way. So this is the force on 2 of 1 on 2. And then it's also touching box 3. So box 3 is actually going to be pushing this way on it. So I want to, this is the force of 3 on 2, right? Well, now I have two forces in this X direction, and I don't know what they are. Yet I do. Because of the third law, I know that the force that 2 exerts on 3 will be, that's 12.5. That's going to be the same as the force that 3 exerts back on 2. It's just going to point the opposite direction. So this force here is that force because of the third law. They're action-reaction partner forces. They're contact forces. Technically, it's a normal force, but I'm calling them something different here. So I don't get, I got normal forces running around all over the place here. So that's 12.5 newtons that way. So now I can solve this. So I sum the forces in the x direction, and that gives me the force of 1 on 2, and that's positive according to my x direction. And then I subtract from that the force of 3 on 2, which is 12.5 newtons. And I set that equal to the mass 2 times the acceleration. But I know what those are. So the only thing I don't know is this 1 on 2. This tells me 1 on 2 is going to be, let me move that on the other side. This is going to, that's m2a plus f3 on 2. This becomes, this is 8 kilograms times 2.5 meters per second squared, and then plus 12.5 newtons. And when I compute that number, I get 32.5 newtons. Okay, so now I know this is 32.5 newtons. Cool, so I'm done. But I want to make sure that I'm consistent with everything with the third law, right? With all the other forces that are internal to here. So let me draw this last free body diagram here. So let's draw box 1 again, and this is the 15 kilogram box, and draw the forces on it. So it feels a normal force up and a gravitational force down, and it feels a 70 Newton push force, and it's also touching the second box. So this is the box force of 2 on 1, right? So that's the force that 2 feels. And what I'm going to do here is I'm going to pretend that I don't know the acceleration, and I'm going to find it and see if it's consistent. I know that this force is the 32.5 Newton force. I know the 70 Newton force, so I know all the forces here. I can find the acceleration. So let me do that. I'm going to again sum the forces in the x direction. Getting pretty good at this by now. 70 newtons, and that's in the positive x direction, minus this 32.55 Newton force. That's going to be ma in the x direction. And the m I'm going to use is the 15 kilogram mass. Okay, so 70 newtons. So if I take 70 newtons minus 32.5 equals, this is 15 kilograms times some unknown acceleration. Now if I divide both sides by that, I find the a as 32.5 over 15. So when I punch that into my calculator, go ahead and try that out. You'll find it to be 2.5 meters per second squared, which is the same as the acceleration I got when I treated them all 3 as one unit. Okay, so let me just recap here because there's a lot going on here. First of all, the forces that box 3 feels from 2, 3 then pushes back on 2 with an equal and opposite force, and we use that over here. Here and here. So this force here and this force here were third law partner forces. Then we again use the third law, that the force that box 2 feels is the same as the force that box 1 feels from 2. And so we use the third law again with this one here. And you'll notice that the third law is completely consistent with the second law, as it has to be, and surely Newton realized this when he was formulating it, which is why he formulated it. All right, hopefully this was useful.